Before we dive into programming, let's take a more careful look at the importance of the problem formulation and representation process by examining a commonly used problem-solving approach called state space representation. In state space representation, a problem is represented as a set of states. I'll use examples to illustrate what I mean by states later on. A state space is a set of all possible states that a problem can be in. In particular, there are a set of initial states, that is, where the problem starts, and a set of final states, including all possible solutions to the problem. Two states are connected if there's a legal operation that can transform one state to another. Let's look at some examples to get a better understanding of the state space representation. This is a simple example. The problem here is the turn on an iPad. There are two states, sleep and operate states, and they are connected by an operation of clicking on the power button. Initially, the iPad is in a sleep state. In order to switch to the operate state, the user clicks the power button. The iPad switches from the sleep state to the operate state. The user can switch the iPad to the sleep state again by clicking on the power button. The previous example probably didn't tell you much about the usefulness of the state space representation. Let's now look at a more interesting example. I'm sure that all of you have played the game of tic-tac-toe before. In the game, two players will take turns to put a cross or circle in an open slot of a 3x3 grid. Whoever gets 3 in a row first, either horizontally, vertically, or diagonally, will be the winner. The simulation here shows two computers playing tic-tac-toe with each other. Since computers don't make mistakes, we can write programs to guarantee that they won't lose in the game of tic-tac-toe. This is the kind of problems studied in the field of artificial intelligence. In this diagram, you can see that the game starts with all the slots open in a 3x3 grid. We call this the start state. Let's say the player who picks the cross starts first. There are 9 possible locations that the first players could place the cross, but because of symmetry, the graph here is showing only 3 choices, including the middle one, which is unique. The corner one represents 4 cases. Similarly, the side also represents 4 cases. The second move would be made by the player who have taken the circle. These are all possible moves for the second player after removing the symmetric cases. If we continue to go through all possible moves, the resulting graph will give us the state space. Guess how many possible states are there? If you are patient enough to trace all the possibilities, you'll find that there are over 250,000 or 250,000 possible move sequences. Instead of going through all these cases, let's further expand just one particular case here. These are all the possible placement of the second clause after these particular selected states. And these are some possible placement of the second circle. The third move of the player with the clause will lead to the first possible winning state. Similarly, the third move for the circle would lead to the first possible winning state for the circle. This is a state that will lead to a draw. These resulting winning states, together with the draw states, formed the set of final states. There are a lot more final states that are not being shown here. At the end of this course, you should be able to write programs for this kind of games or even more complex problems.